So today we'll be talking about the signal processing palette. In the signal processing palette live a lot of functions: the waveform generation functions, the waveform conditioning functions, the waveform measurement functions, some signal generation functions, filters, spectral measurements, transforms, FFTs point by point, and the digital filter design toolkit, which is what we are going to be focusing on today. So filters primarily serve two purposes. One would be signal separation, and two would be signal generation. So if I were to illustrate what signal separation would mean, so a child in the womb is constantly monitored for the heartbeat. So there needs to be some electrical measurement devices which monitor the heartbeat of a child in the womb. But what you notice is that along with the heartbeat of the child, you also have the heartbeat of the mother and some signals which are produced while breathing interfering with the signal that you are interested in. Now, in the presence of those signals which are interfering with the signal that is desired, you need something like a filter which gives you your desired signal. Another application would be signal restoration. So what you have in front of you are different forms of an image. On the upper left corner is the original image, and once the original image is passed through a low-pass filter, a high-pass filter, or an extremely high-pass filter that gives you a sharpened image, you see different responses. So extracting information that has perhaps been hidden because of the superimposition, noise, and various other interfering signals that could be in the surrounding. So these are primarily the two major roles of filters and where you would actually require a filter in signal processing. Now when I talk of filters, it could be analog, it could be digital. And right now, we choose to tell you about the digital filter design for all obvious reasons why digital signal processing is preferred over analog signal processing. If I were to explain a filter to you, you would ask me to explain it to you in three forms, either through an impulse response, or through a frequency response, or through a step response. So briefly telling you about each, the impulse response would be the output from a filter when the input is an impulse function. The step response will be for an input which is a step function. Now because the step function is an integral of the impulse function, similarly the step response could be acquired by taking an integral of the impulse response itself. And the frequency response would be simple, an FFT of the impulse response. You could also change the scale from linear to logarithmic. So if you have a frequency response, all you need to do is change the scale of the x-axis from linear to logarithmic, and what you get is a frequency response in dB. Now, when we talk about implementation of a digital design filter, there are primarily two ways. One would be convolution, and the other would be recursion. So what we get through convolution is a finite impulse response, and what we get through a recursion is an infinite impulse response. So let me just give you a quick look into each one of those. So when I talk of an FIR filter, it's defined by the equation which is right in front of you. Now in this equation, if you look carefully, it's the output, which is Ym, is dependent on the current input and the previous inputs. And each of these inputs is being multiplied by a coefficient and then added. So the dependence is only on the current and the previous inputs. Now if I take a transform of the same, what I'm going to get is a transfer function with a numerator. So the numerator defines the poles and the denominator defines the zeros. Now because I don't have the zeros in this case, so it will be a more stable response as compared to a transfer function with both numerator and denominator, which you're going to see ahead in IIR. Now generally we prefer to use FIR filters when you have applications that want linearity in the phase. So when the application demands a linearity in phase, you would want to go with an FIR filter. However, if you had a requirement where you want to extrapolate on the traditional analog filters, then what you would like to choose would be an IIR filter. An IIR filter is defined by the equation right in front of you. So if we look closely into this equation, the IIR filter is not only dependent on the current and the previous, the previous inputs, but also on the previous outputs. So How would we get that kind of dependence? Through a feedback. So that's the equation which defines the IIR filter, which is right in front of you. And in this case, if we go for a transform, we will see that there is both a numerator and a denominator. It would have poles and zeros. Now, because it has zeros, that brings in the instability in the filter. Now, implementation wise, if I were to talk about implementation onto an electronic circuit, of course we would prefer the IIR filters because they would be cheaper to develop. There would be lesser electronic component that would be required, and there would be so let me just quickly tell you a few of the criteria that you would have to keep in your mind when you are given a task to design a filter. Firstly, study the transfer function. After studying the transfer function, the second thing that you're supposed to do is the memory usage. How much memory are you allowed to use on the electronic circuit? Excuse me. The third criteria would be the coefficients. So again, the number of coefficients that you have would also again decide the requirement of the memory. Third is the requirement of linearity, whether linearity is required or not. Now, apart from these FIR and IIR filters, we have a lot of other categories in which we classify the filters. For example, a low pass, a high pass, a band stop, a notch, a comb filter, a ripple filter, which, as the name suggests, performs the functions. Now, all of these filter designs and functions are allowed on LabVIEW through the Digital Filter Design Toolkit. Now, a Digital Filter Design Toolkit is an add-on. So for all of you who have the existing versions of LabVIEW, the licensed versions of LabVIEW, or the evaluation versions of LabVIEW, you might not have this Digital Filter Design Toolkit might not appear in your signal processing palette. So what I am going to recommend to you is that download it, use the evaluation version, right? And for the contest that's going to come up for this week, use it, and you can run it in the evaluation version and send us the code. If you like it, go ahead and purchase it. So how about implementing whatever I said on LabVIEW and having a look how to program it? So what I've done is I've made some simple programs for you. And I'm going to start off with an FIR filter design. Now when I talk of an FIR filter design, there would be some important information that you would have to give to me before you tell me to design that. Firstly, you would have to tell me what is the filter type. Now when I talk of a filter type, let's just play around this enum and see what all options are there. There is the low pass filter, which allows frequencies below a cutoff, a high pass filter, which allows frequencies beyond a cutoff, a band pass filter, which allows frequencies within the cutoffs, and band stop, which does not allow frequencies within the cutoffs. Now, the number of taps would in turn decide the order in an FIR filter, which would again decide the coefficients, which would again decide the memory usage on the FIR filter. Now, one of the most common ways of implementing an FIR filter is through windowing. So when I talk of windowing, LabVIEW offers you a host of windows. For example, the Hanning window, the Hamming window, triangular, Blackman, the other versions of Blackman, the flat top. Then, of course, the sampling frequency of the signal that you're going to be putting in as input, and the cutoff, which is the lower cutoff frequency, and the higher cutoff frequency. Now, let's quickly run this code. See the response, the magnitude as well as the phase response. Now, what we have, the first error that we have is a band pass filter, okay? And the window that I'm using is a Hamming window. Now, let's just quickly see what happens with the type of the filter. So now, this time around, what I'm using is a low pass filter. The low pass filter, as you see, starts falling down from 150. Now, it starts falling down and it slowly comes down. So that's basically the steepness of the roll-off, right? So the roll-off factor is something which is decided by the window that you're using. So different windows, and I see that the roll-off changes. Now you have high pass. Similarly, you have band stop, which gives you basically a notch. So if you were to get a notch filter, you would have multiple band stop filters connected in a cascaded manner. And you could change the cutoff frequency, you could change the high cutoff frequency. Let's just quickly go to the block diagram and see how easy or difficult the implementation of it was. Now, what I'm doing over here is primarily using just two functions to get the entire functionality. Now this is a case structure. This case structure has been defined for all the different windows that you were seeing. So you were seeing all those different windows like Blackman, Hamming, all of those. You have predefined VIs for all of these. So what I've done is I've clicked on sub VI and I've gone for context help. And this is the DFD, which is Digital Filter Design Window, FIR design sub VI. Now this sub VI requires the window, so wherein you choose what type of window it is, the filter type, whether low pass, high pass, band stop, the order, which would decide the number of taps, the high cutoff frequency, the low cutoff frequency, the sampling frequency, and what it gives you out is a filter. Now, this filter could be used and convolved with an input signal to get the output signal of any transfer function that you desire. The second sub VI, so once you have the filter out from here, all that you're going to do is define that filter. So like I told you while I was speaking about the filters, that the filter characteristics could be of three types. One is an impulse response, or a step response, or a frequency response. So what we have here is the frequency response. So the frequency response is giving me both the magnitude response and the phase response. I could have also had an impulse response over here or a step response over here. So just two simple steps in LabVIEW whenever you're doing a digital filter design. First one, choose the window with which you're going to implement the FIR filter. And step two would be to get the characteristics out, frequency response, impulse response. And also another suggestion would be that whenever you're going for choosing different windows, for example, you have these different windows listed out here. This is what I'm talking about. So how do these differ? So primarily there are three features how we differentiate between these windows, either through the side lobe width or to the main lobe width, and we have the roll-off factor. So these three characteristics are different for different windows. Depending on what and how you require in your application, you can choose any one of these. This could either be through a deterministic manner where you know it beforehand, what is it that you require, or it could be through an experimental manner, wherein you could see the response, make calculations. So there is the digital filter design also allows you a filter analysis tool. Through filter analysis, you can do analysis on all of these different, the response that comes out from all of these different windows, and see for yourself what suits you best. So this was about the finite impulse response design. Now let me show you the infinite impulse response design. Now, when I talk of the infinite impulse response, again, like I demanded from you, what are the different characteristics or what are the different requirements that you have for the filter? Similarly, you need to tell us here the type of filter, which is same as in the previous case. Now, the point is that when you go on for an implementation of an IIR, you have the traditional analog designs, filter designs to take and implement. So IIR does not allow you as much as flexibility as does FIR. So let's just quickly see what are the different types. There's Butterworth, there's Chebyshev, there's elliptical, and there's bezel. So what we're going to do is we're going to be studying all of these again. Let me first quickly run the code and see how it happens. The default, what I would like to set is Butterworth. And you can quickly have a look at, see, I've defined the order. Let me put an order higher than this because it's too small an order. Yeah, I think I'll put 30. And okay, let's just run the code. Right, so what I have in front of me is a Butterworth response. Now, we all know that Butterworth response is maximally flat response in the pass band. So like we can see, it's a maximally flat response in the pass band. And we also see that the phase response is not linear, so that's why we don't prefer to use IIR filters for linear applications. Now, let me just quickly change it to Chebyshev. Now, when I take it to Chebyshev, we know that by studying the transfer function of a Chebyshev filter, it allows ripples in the pass band, and that is what we see over here. However, one difference from Butterworth is that the roll-off is more steep. So you see that the roll-off factor is steeper than the Butterworth filter. Now, let me take you to inverse Chebyshev is again an extrapolation of the same. I'll go to elliptic. So when I take elliptic, now elliptic allows ripples both in the pass band and in the stop band, and this is what we see over here. So this is the elliptic design, and finally we have the Bezel. Now, Bezel filter design allows maximally flat response in the pass band, and it also allows a linearity of phase in the pass band. So when you see the pass band, in the pass design there is linearity of phase, right? So again, we saw it looks simple on the block diagram. Front panel. Let's just quickly explore if it's as simple on the block diagram. Now, when I talk of the block diagram, there are again two simple FIRs that I have used. This is the case structure, which has been defined for each of these different filter operations. There's the Butterworth. Again, let's just open the context help and see. So you have to define the filter type. By filter type, you mean low, high, band stop, or band pass. The order, the high cutoff, the low cutoff, and the sampling frequency. And what we get as far as the filter out, that filter out could be used to plot, again, using magnitude response and phase response. And also, one of the inputs which I'd like you to notice here is dB on question mark. So this basically tells us the unit that you want for the power. Again, you could want it in dB, then you could have a linear scale or you could have a logarithmic scale. So this is from where you get the flexibility. Now, so this was about infinite impulse response. Now, once we have the filter designed with us, once we've designed these filters, we need to know how to use it with the impulse, with the input signal, so as to get the output response. Now, there would be a convolution. So what I'm going to do is I'm going to show you a very simple application that I've made for extracting information from a given signal using a filter operation. It's pretty straightforward and shouldn't take much time to show. So let me just quickly run this code. And when I run this code, you see two kinds of graphs. There's the white graph and there's the red graph. And my graph palette tells me that the white line denotes the original signal and the red line denotes the filtered signal. So if I look at this signal, I see that the white signal is a composition of a lot of sine waves and cosine waves, merged into each other. Now, what I'm doing is I'm using a filter to extract just one of those sine tones, which add up to the white original signal. Now, how would I do that is as simple as this. So if I concentrate this part, which I've highlighted, this is nothing but generation of that multi-tone signal. So all this part, all that added part does is just a signal, which is a multi-tone signal and has a lot of sine waves and cosine waves added into each other. Now, once I have this becomes my input signal, and this input signal has to be convolved with the filter so as to get the output. So what I've done here is I've used a simple VI, which is the DFT classic design filter. So it's a built-in filter that you have. This built-in filter requires some inputs on your end. It just asks you whether you want whether you have the ripples, if you want to allow the ripples, or it also asks you about the the sampling frequency. And it asks you about the type of filter which you want, and it asks you about the design method. What is the kind of equation or difference equation that you will be using to implement that filter? And what it gives out is a filter output. Now, this filter output is then fed into this sub-VI, which is called the DFD filtering sub-VI. Now, this sub-VI takes two inputs. One is the signal in, which becomes your input signal. Another is the filter. So these two signals, we all remember the equation which says Ys is equal to Hs into Xs. Now, the Xs becomes the input signal, and the system response is convolved, and what you get is the output signal. The output signal, which is this wire, is then fed into the graph. So the graph goes to fed, which is the output, which I run once again to show you. So as simple as that. So if I were to sum up everything for you, I would say that how you would generally go about developing or designing a filter would be, firstly, to know the kind of application you have. Now, in that kind of application, you'll have to figure out the type of filter that you'll be using, whether you want to be dealing with a pass band, or whether you want to deal with multiple frequencies, wherein you could use something like a comb or a notch, or you would, for example, if you were more into image processing, you would want to use tools that can enhance your images by sharpening them more, making the edges more clear, or making the contour better. So once you figure out what kind of application you have, the next step would be designing a system response for it. So when I say designing a system in response for it, you would write down a difference equation. Once you have the difference equation, you could take the transform of it to get a transfer function. Once you have a transfer function, you can calculate the coefficients that you may require for the filter development. Once you have the coefficients for filter development, you could go on to design a filter response. So, and then when you have the filter response, you have the input signal, you convolve the two with each other, and then you get the output response. So that would be an ideal way of going about the filter design toolkit. And the questions that we have today are pretty much based on the same algorithm. So I hope you heard me clearly. And so switching back to my slides, which will take a moment. All right. So, like you all know, week after week, we have these contests where a number of participants get involved in solving questions that we design based on, the respective week's topic. Like all the previous weeks, we had a very overwhelming response for the contest number 17, which was held previous to previous week, which is 28th of August. And the winner of this contest, there are two of them. One is Mr. Prashant Patel and the other is Mr. Parth. I congratulate you and I thank you for being so active in not only this webcast but in all the previous ones. And I hope that we can keep up your spirits by giving you questions that challenge you and that excite you. So you will be receiving a personal message in your NI community which will be informing you about the same that I've just spoken here, the results of the contest. So last week was very special for the community of Webcast Wednesday when we had Dr. James Trusher with us, and we had Jagriti interview Dr. James Trusher, and we shared a lot of questions that you had asked and what you want to know from him, and I'm delighted to say that he did answer all of them to the best. And another important thing was that James Trusher rewarded one of our actively participating members in the Webcast Wednesday community, like we promised to you. So what you can do is, if unfortunately due to some reasons you missed out on watching this session, we have archived it for you, and you could go on to the LabVIEW enabled community, and therein you'll find the archived session wherein you could view it. So what we have here is one of the active members of the Webcast Wednesday community being rewarded by Dr. James Trusher. Now, he has attended all episodes of Webcast. I'm sorry. Yeah. I think I'll just take water. Sorry. So yes, Mr. Prashant Renuka, he has been attending all episodes of Webcast Wednesday, and he also volunteered at the Webcast Wednesday stand on NI Days. And here we have Dr. James Trusher rewarding him with the certificate of participation. Apart from him, we have a lot of other members who've been extremely active in the LabVIEW Webcast Wednesday questions that we were posting week after week. And I would like to give a special mention to all of them. Mr. Parth, Mr. PVP, Ms. Shweta, Mr. Ganesh Murthy, Mr. Ahmed, Mr. Amuri, Mr. Himanshu, Mr. Saksaitin, Mr. Bakyaraj, Mr. Sagar Doshi, and Mr. Rahul. You will be soon getting a mail from our end wherein we'll be asking you about your postal address, and we'll be giving you personally signed certificates by Dr. James Trusher. Thanks a lot once again for being so active, and we hope that you stay active in due course. So coming on to the contest of the week, now I'll be telling you the questions for this week's contest, and as soon as I tell them, the link to these questions will be sent to you on your personal messages. So question number 1 is, you have the image in front of you. Now, when you look at the image, you see two parts of the image. The upper part shows you the original signal, and the lower part shows you the filtered signal. Well, this is all that we are going to tell you about this. What you have to do for us is design a VI that gives you a front panel which resembles the image as shown. So, I mean, not just the image, you of course need to have functionality on your block diagram which does the same for you. So this is all that we'd like to say about this. Once again, I'll repeat. So the original signal is given to you, which becomes your input. The filtered signal is an output. Now, how you get to the filtered signal from the original signal using the DFD toolkit is what you have to tell us. This is question number 1. So for those of you who've been working extensively in LabVIEW and who would like to be challenged more, we have the second question. So what you see is a differential equation. Now, studying and analyzing this differential equation, you have to tell us whether I think there is some sound technicality issue. Just give me a moment while I resolve it. So if you cannot hear me, kindly message us so that we come to know. And I shall resume now. So once again, the second question shows you a differential equation. Now what you have to do for us is analyze this differential equation and tell us what is it that you're going to be using, an FIR or an IIR. Now, you could write the reason for it in the community post, wherein you're going to be posting your VIs. So just have a line for what is the reason for the same. The second is that you will design a transfer function using LabVIEW. So when I say a transfer function, you'll have to use a transform like the word suggests, and you have to give me the transfer function that defines the differential equation as given above. Now once you have the transfer function, I want you to extract the parameters, the H parameters from the transfer function and use it to design a digital filter. So I'll break the question down again to you in simple words. You have the difference equation right in front of you. The first question is a conceptual question wherein you tell me what kind of a filter you will be designing, whether an FIR or an IIR filter. The second question would be to find the transfer function of the same differential equation using LabVIEW. And the third question would be use the transfer function to design a digital filter, again using LabVIEW. So a little bit of hint to you. In the digital filter design toolkit, you have the FIR palette and the IIR palette. Once you've figured out what kind of filter it is, whether an FIR or an IIR, you can further delve into any one of these palettes. Now when you go into these palettes, you'll have a host of other functions or sub-VIs available to you. So there will be sub-VIs that will use the H parameters to design a filter for you. That is something which I would like you to explore. Now, the question should be live and you should be getting a message in the form of a link to the contest. I would request you all to go through the link, study the question well, start solving it, and start posting the answers. The sooner you start answering, the more time we have to give you our feedbacks, and the better chance you have of winning the contest. Now, what you could also do is log on to www.labviewenenabled.in. When you go over here, you can watch the previous episodes of Webcast Wednesday. All the previous episodes of Webcast Wednesday have been archived. They are on various different kinds of issues, which which you would like, which may play handy in your applications. Or you could have your own queries from the different sessions of LabVIEW that you've seen, or the Webcast Wednesday that you've seen. You could post those queries over there, and our applications engineers would love to help you out with them by answering them. You could, so like we said, we call it the Webcast Wednesday community because everybody interacts with each other. We've seen people interacting amongst each other when they answer the questions, helping each other out in making better applications, pointing out suggestions, faults mostly. And what is the incentive? The incentive is that you participate in weekly contests here and win up to 50% discount in the CLAD exam and other National Instrument Certification examinations. And there's also the incentive of attending 20 webcast sessions to win a free CLAD attempt. So if you guys are watching, if you guys have been watching it continuously for 20 webcast sessions, we are keeping a track of all of you, and we'll be sending you a mail wherein you can get an attempt for CLAD free. So don't miss to log on www.labviewenenabled.in, and in case you missed a part of this session or you would like to view it again so as to get a better clarity on how to solve the questions, go on to www.labviewenenabled.in, and this session will also be archived and will be put on it say by tomorrow morning, and that's it. So it was great on my end to be sharing this session with you. Hope to see you again next Wednesday, and all the best for the contest.